All right. Hello, everyone. How's everyone feeling? Oh, yeah. It's 4:45, 5:15. Okay. So we have a small group here today, not expecting that many more people. So anybody at the back who wants to come front, like, feel free. So we have two great presenters today, both researchers on campus. I've done a lot of research. And so it should be pretty exciting presentations. Each of them will be presenting for about 20 minutes each with 10 minutes of Q&A. So the way we're going to do this is Sebastian's going to go first, give a presentation, and then we have 10 minutes of Q&A, and then Sean's going to come up and then blow your minds, and then you have about 10 minutes of Q&A as well after that. So I'll give a short description here of Sebastian and Sean. So the title of Sebastian's talk is Peer Effects on the Diffusion of Solar Panels, a Dynamic Discrete Choice Approach. His research lies in the broad area of data-driven optimization, statistics, and economic modeling in operations and management science. In the last couple of years, he's been studying the factors that influence residential energy consumption, and in particular, the adoption of solar photovoltaic systems with the goal of designing public and private interventions to incentivize efficient energy use. He's a PhD candidate in supply chain and operations management at the McCombs School of Business, and over here. He received his MPhil in operations management from NYU and his BS and MS degrees in industrial engineering from the University of Chile. He also has an awesome website, which is www.souyris.com. So you want to check out more about his research is there. Secondly, we have Sean Wood, who's going to be talking about looking towards higher capacity anode materials for lithium-ion batteries. He's a fifth-year PhD student in chemical engineering. He works under Dr. Buddy Mullins and Dr. Adam Heller. He holds a National Defense Science and Engineering Graduate Fellowship. His research on lithium-ion battery materials aims to make them charge faster and last longer while also improving their safety and cost. Outside of his research, he enjoys volunteering at events that introduce children to basic concepts of science and engineering so that they may one day be inspired to join these fields themselves. So please give a big hand for them. And Sebastian.
Thank you very much for the introduction, and thank you to everyone for coming today. And this project that I will present today is something that I have been working on from about 2 years, and starting that I joined the group of Dr. Rai, that he has like more than two, about 4 or 5 years working with trying to understand the solar industry. And I will present a project that is under that umbrella. So apart from Dr. Wright, I am working with Professor Jason Duan, who is from the marketing department at the business school, and Anand Balakrishnan from operation management. So the problem that we wanted to understand and study is the residential, why people, households install panels. What is their incentives and motivation to install panels? So if we look about how the prices of installation have been during the history in the last decade, we already saw a couple of presentations before, and probably you already know that the price have been decreasing almost by more than a half during the last decade. So that looks like, okay, there is a big economic incentive to install panels. But at the same time, if we look at the incentives that the federal and the states give to the consumers to install panels, it follows like the same kind of trends than the prices itself. So at the end, if we take the difference between the incentives and the price, or the price minus incentives, the reduction is not that much. It goes from about a little bit more than $8 per watt on capacity until $6. So that is like until 2013. Today the prices are lower, but this is more or less the last decade. So the economic incentives is there, but it's not that much if we see what is really the capacity that have been installed. So these curves show the total capacity for the residential consumers that happen year by year. So this is not cumulative, it's year by year new installations. So we see that until 2006 it was kind of flat, the trend, but then there is an increase that looks like an exponential increase. So our question is that why this happens, because as we saw before, there is some economic incentives, but it's not that much to explain like this increase in 2006 to have this kind of exponential curve of installations. So that is our main question, why this happens. So to understand that, we will focus on here in Austin. And this, we can see here that we have this black line shows the area of the Austin Energy Service Area. And as you know, here in Austin, we have only one big utility, which is Austin Energy, that offer electricity for us, the consumers. And except from, you know, here at the university that is provided we have our own power plant. But the rest of Austin is a special case. Here there is another competitive market, there is just one utility. So it's an ideal city to study the comparison of having electricity from the utility versus having electricity from the solar panels. So these red dots are all the installation until half of 2013, July 2013. So if we go and see more in detail, this is the same map that is divided by block groups. Here we have the first group of households that installed until 2005, and then we see what happened 2006, 2007, and then we have there what happened in 2008, 2009, and if we started to see this map and these dynamics in a little more detail, we will see something like this one. So I would like you to put their attention in this blue circle. In this blue circle, we just have a new group of households that installed. That cumulative red points that we have there, that just happened in the last year. And then if we see what happened in the next couple of years, there's a big increase. So from let me come back there, from nothing to something to boom. So it looks like a kind of clustering phenomena, kind of similar to what could happen from a disease spread. Somebody got this infection and boom, then that explodes. So at the beginning we took that kind of approach and tried to use models about diffusion of disease to try to model this type of phenomena. And when we realized that it's really nice, but it didn't capture really well a looking forward kind of way that the consumers see the panels. That is what I will explain during the whole talk. So this is the phenomena that we want to do to study. Somebody installed, and then the rest of the neighbors started to see, oh, this looks nice, maybe I should install. So that is what happened later. So our research questions are, the main research question is, what is the drivers of adoption? What are the drivers? So there is economic drivers, there is this peer effects phenomena that seems to happen, and we wanted to confirm that actually that previous study that showed that Dr. Wright have a previous study with a fellow student, Scott Robinson, that studied this phenomena using agent-based models. And we are doing something, so they show that there is some Peirce effect. What we wanted to show in this research is that apart from the Peirce effect, there is a phenomena that the household see what happened right now, what are the prices that right now are available, and then look to the future. Should I install now, or maybe should I install in the future with better prices? So that is what we wanted to put into our model. And our contribution is exactly that. Study what are these contrafactual analysis that could do the household, the economic study about installing panel now or to the future, put into the model the Peirce effect, this forward-looking mind, and put all of that into a structural model, which is what I will show during the rest of the talk. The idea of a structural model, the main advantage of a structural model is that captures the preference of the consumers. And that is because we model the utility of installing something, of adopting or not adopting in this case. So that is the model that I will present. But why we wanted to do that? Because this will allow us to the future then do contrafactual analysis about policies. So what will happen if we offer to consumers certain incentive. Right now there is incentive to install a system. If you go to the Austin Energy webpage, it will tell you for this capacity, for each watt of capacity that you install, we will offer a certain amount of dollars. So what happens if we change this amount? What will happen if we offer a different schedule of incentives? So that is the type of question that we would like to answer at the very end. But what I will show now is the model about the diffusion itself, without doing the contrafactual analysis. That is a second part of the research. So in order to create this model, we have been running a survey that has already 3 years of runs of surveys to all the households that install panels on Texas. So we have a pretty good response rate. About 30% of the households have been answering this survey. So each survey has been a little bit tailored, a little bit better year by year. We have been learning how to do this survey. And we make questions about how you get the type of question that we make is how you get information about the panels. If there was some neighbor that bring your attention to install the panel. If it was installers, what are your environmental concerns? What are your political position? Question of that kind. So at the end, we took the survey and analyzed it and come up with this kind of behavior of installation, behavior that the consumer have to install a panel. So at the beginning, we have a consumer that doesn't have, or household doesn't have the panel installed, and probably have some initial attitude toward the technology that we don't know as a researcher. But there is something, the only thing that we know is that they live in certain position and nobody else installed around there so far. So in the next period, somebody installed. This person see what is going on there, they got their attention, and then the person could start to think about it. Maybe he's started to think about it, maybe not, but at least is aware about this technology. Then in the next period, this person, there is more installation around in the neighbors, so some of them are closer, others are farther, and this person started to wondering, maybe I should install, and started to be a more serious analysis about this, should I install now or maybe install in the future. So it's influenced by the previous installations. Then at certain period, the person decides to install. So they say, yeah, I will install. And go to Austin Energy and apply to the program. Apply to the program and says, I want to install, and then there is a process that takes about 6 months until the person got the system installed. So that is what really happened. First, the person goes to, and apply to this program, and then about 6 months after, the person got to install the system. This is what happened, and this is really nice for us, because allow us to disentangle this problem about who influences whom. Because we see that if we don't have this data at the moment of installation, at the moment of decision of installation, we cannot say maybe this guy's installed and then the next day our household install, and we cannot know who influences whom. Maybe it was him that was having this conversation with this guy, but just by chance he installed later. So now we can disentangle this time difference between decision of installation and installation itself, and we can separate this, that is called reflection effect, who influencing whom. So we cover that problem. So now, we have this household, we have the history of installation around the household by distance. So the question that the question that the household make to himself is, do I install now or wait to the future? And the information that the household have is the economic factors, taking into consideration the economic factors, taking into consideration the previous installations, and see if maybe these installations influence this household, and the household characteristic itself. Some of these characteristics we observe, because we have some data that I will show what we have, and some of them we don't observe. So the economic factors are the saving in electricity for the future, because when you install a panel, you started to receive some rates of, for the electricity that is produced for the panel, the Austin Energy, and in general, we can talk about at a national level, the utility started to pay you for producing this electricity. There are certain differences in each state by state, city by city, but more or less is like that. utility started to pay you for the electricity that you produce. Minus that, there is a benefit that is obtained from the system, minus the cost of installing, compare that against the wait for lower electricity costs. So should I install now or wait to the future for better installation costs? And also the influence from the previous installation, what is we separate them for the households that are very close, the ones that are a little farther, and the ones that are even more farther. So we create radio rings around this, the household, each of the households. So the data that we have, that we are using in this research, one piece is given by Austin Energy, which is the history of installations and the specific address of each of the adapters, the application dates and cost, and the system specifications. The second piece is data that we got from the city of Austin. That we have the parcel data about all the other households. So we have the full market. And some of these one definitely will never adopt, or in the household here in Austin. Others maybe will adopt. So we have each of the address. We have the house value of each of these houses, and we have the land size. So we can also, and we have also the free cover. So we can compute what is more or less the electricity that can be produced for a given system. So depending on how much shade the houses have on top, it will produce more or less electricity. And the third piece is some segmentation data that allow us to separate the household. So by segment. One more time. Oh, Jesus. So we separate the household in two different segmentation. One is by urbanization, and another is by the economic segmentation. So the model is we separate all the data that we will see right now are for some data that we observe, other data that we don't observe, some parameters that we will estimate, some policy parameters, the electricity rate, and also the incentives that are given to the households, and other data. So the adopter at time t can adopt or cannot adopt. So the utility for adopting is we are modeling this as a base level. That is something that we have to estimate for all the consumers, the same base level. Then the utility that's obtaining for installing the system, which is the net present value of the system, that is the electricity that coming from the saving for electricity that is producing by the system, minus the cost of the system. Also the influence from the previous installation. So we have here this vector gamma, that is a vector that is multiplied for each of the number of adopters on each of these radio rings, and certain heterogeneity that we don't observe, and that is for each of the households is different, and certain utility that is syncretic shock, that is something that is used typically for this type of models and represents something that happened for that household in that particular time period that we don't observe. So we have the net present value that is depending on these parameters that are the solar rate, the cost of installing the system, the rebate, and the system size. And we assume that the utility that for not installing is equal to some idiosyncratic shock. Well, but that is what happened at time t. Then if you let me put off these parameters, separated them in these four categories. So what happened for the household at time t, where he will decide or she will decide. So we have a value function that defines that this value function, which is the utility to go for installing now. If install now, it will obtain certain utility. If it doesn't install, then it will decide if install in the future or not. So if install now, the person will obtain that utility, and if it doesn't install, it will obtain the utility for non-installing, plus the expected value of the future utility. So this is the forward-looking behavior, deciding to install now or not installing. So we have the household compute an expected value for of the value function to go. So we assume certain stochasticity process for the parameters that we don't observe, and for the one that we observe we and the household observe, for example, the cost of installation. The CT is the cost of installation. They observe the history of the cost of installation, and they make some kind of forecast to the future. So we make some assumption about what is the forecast that the household make. So those are reflecting for these stochastic processes. And we compute the likelihood in a very standard way, which is the probability of each of the households that adopt the path of adoption. For one in particular is non-adopt, 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 and at some point adopt. So we multiply all of them. We multiply the ones that didn't adopt, which is just the probability of didn't adopt until type t, and we find the parameters that maximize this likelihood function. So because we have so many these black points in this right side are the households that didn't adopt. Because we have so many, and put all of them into the likelihood function, that will be too much to estimate. We make some clusters of these non-adopters, and we compress them into just one big household. So that is what at the end we got with this black dot that we have in the left side. So this is, for example, the type of aggregation. We aggregate all these black dots into green points. To do estimation of the parameters, we do some Bayesian inference that allow us to do this in a very neat way. And at the end, we obtain exactly what we're supposed to obtain. For example, here I'm showing the parameters for the influence for the urban and rural household. So let's focus first on the urban. We got parameters that this gamma 0.25 are the influence that for one household, the influence that go one household for all the adopters that already exist at a quarter of a mile around them. So then this gamma 0.5 are all the households that are a radius of half a mile around. And then 1 mile. So we see what intuitively you will think what happened is that, okay, the ones that are closer give more influence than the ones that are a little bit farther, and then all the rest, which actually our estimation says that is almost zero. The influence that the ones that are really far away, the influence that got from people that are far is almost zero. So this intuition that you will have, okay, is obvious. We got more influence for the guys that are really close. That is obvious. But the nice thing about this one is that we are able to compute, to measure. So this research is a research that allows us to measure this. So we are creating a rule. We are creating a measuring device that allows us to estimate these parameters. And because how is this, we estimate this parameter is taking into account the preference of the household. These parameters don't depend on the actual data, on the actual history of data. It doesn't depend on the cost. It doesn't depend on the rates of solar. So if we change the rates and we change the price of installation, we are able to make a forecast of what will be the path of diffusion. So this is a property of this type of model that are called structural modeling. Well, the same type of parameters we obtain for rural households. So well, that is the research, and the takeaways is that we have this this technology, this device that allow us to estimate what are the parameters that define the utility function of the household, and with them we can make contrafactual analysis about what are the policies that you can have in order to reach the diffusion goals that could have. In this case is Austin energy, but you can apply to different kind of solar contexts. Solar in different, it could be a solar at a level of a state, or maybe in different cities. So yeah, thank you very much.
About 5 minutes for Q&A.
Thank you for the wonderful talk. It was amazing. And so I had a question. What do you have to say about the difference in the first, in the 0.25 mile effect comparison of urban and rural areas? I mean, it was really surprising because I thought that one would think that in urban areas, sort of, you would have a more impact because of, yeah, so.
Yeah, we think that this big difference is because in rural areas you see less, you have less people around you. So because you have less people around you, is that if something happened to your neighbor, you get your attention got quickly to that guy because you have so few people around you. So it's also a reflection of that. Yeah, good eye to observe it, that point. So. So it's interesting to see. It's reflected by the model. Mm-hmm. Thank you for the question.
Anybody else? All right, well, Sebastian's going to be here after as well, so if you have any questions later, feel free to talk to Sebastian. He'll be over here. So Sean, if you want to go ahead.
Thank you.
Great. Hey, everyone. I'm Sean Wood. I'm a fifth-year PhD student in the chemical engineering department, but really my research isn't so much chemical engineering as it is material science and electrochemistry. So I work for Dr. Buddy Mullins and Dr. Adam Heller on lithium-ion batteries. And so we're looking towards making higher capacity anode materials for these lithium-ion batteries. And so as a scientist, a lot of what I do is very technical, and as an engineer, I like to put numbers to things. So here's kind of, as you go through my slides, how technical is each slide. So for you who are wondering, when you get to take a nap, I would recommend these slides. So why are batteries important? I think everyone already knows the answer to that question. They're in everything. They're in cell phones, laptops. Nowadays we have wearables like the Fitbit. And so this data shows how much lithium has been used throughout the years for the last 2.5 decades or so. And you can see that the production of lithium worldwide has increased by about a factor of 3. And as we start moving towards things like electric vehicles and grid storage, that number is going to keep going up and up and up. And so we need to kind of update the technology to keep up with the increasing demand for lithium-ion batteries. So I'll go over briefly how a lithium-ion battery works on a very simple level. So you have your positive side and your negative side. The positive side is the cathode, which is shown here in purple. And typically that's a layered material called lithium cobalt oxide. And then on the right side you have the anode material, which is usually graphite, which is also a layered material. And so when your battery is empty, all of the lithium is stored on the cathode side. And then when you start to charge your battery, you move those lithiums over into the graphite. And then when you actually want to use your battery to power something like your cell phone, the opposite occurs. You move that lithium back from your anode back into your cathode, and that drains your battery. So this is the current state of materials that are used in lithium-ion batteries. So the graphite and the lithium cobalt oxide I just mentioned are down here and over here. And so you see those are pretty low capacity materials compared to some of these other materials that are up there. As we move forward, we want to start pushing these materials to the right in terms of capacity so that we get higher capacity. Capacity is just the number of lithiums that you can store per weight of material. And then you have a potential, so the cathode materials have a high potential versus lithium, and anode materials have a low potential. And if you subtract those two numbers, that's your overall battery voltage. And so as we start getting into the higher voltage cathode materials like sulfur and air, you can see that their potential is a little bit lower, and so that means our overall battery voltage will be a little bit lower. It turns out that doesn't really matter as much because when you look at energy density, that's your capacity times your voltage. And so even though we cut the voltage in half by about 2, we're still increasing the capacity by a factor of almost 10. And so when you multiply those two numbers together, you still get a massive increase in energy density. So these materials here on the left are where we've kind of been for the last 25 years or so. Graphite and lithium cobalt oxide have been the materials in lithium-ion batteries since about 1991. And there haven't been too many improvements in those materials since then. As we go forward, as I said, we want to go towards these higher capacity materials, specifically sulfur and air for cathodes, and ideally silicon and lithium for the anode side. As I said, we have had these materials for the last 25 years or so. So anytime you see articles in the news about the newest, greatest battery technology, you should be a little bit wary of that, because a lot of times they contain a lot of hype. And so what do I mean when I say hype? So dictionary.com says it's to intensify the advertising, promotion, or publicity by ingenious or questionable claims. If you go to Urban Dictionary, which is a little bit more understandable, it's a clever marketing strategy in which a product is advertised as the thing everyone must have to the point where people begin to feel that they need to consume it. And to these definitions, I would add it's basically selectively omitting the negative information and only kind of showing the positive side of your material to make it seem better than it is. So what are some examples of this? Here's some article titles I pulled that are related to batteries. The first two kind of make these grandiose claims about, charging in seconds, lasting months. MIT says they can come up with one that has almost an infinite lifetime. That seems too good to be true. The next three use words and phrases that are kind of familiar to everybody to kind of grab your attention. Words like holy grail, fool's gold, sugar. The idea of a sugar battery that can run 10 times longer than a lithium battery sounds pretty awesome, but you kind of have to dig deeper and see if that's actually true. And this last one is my favorite. Forgetful scientists accidentally quadruple lithium-ion battery lifespan. Oops. So where does my research fall? I'm studying two materials that I'll talk about today. The first one here is lead. And you can see that's kind of close to graphite, and it's only an incremental change. So why would I want to look at this material? So there's a couple different motivations. The first is academic. It's a relatively understudied material compared to these other popular materials that I showed on the chart. For instance, there's about 2,000 papers on silicon and only about 20 papers on lead. So this is an area as a grad student that would be pretty good to explore. And then in terms of practical motivation, it does have a higher capacity than graphite. It may have other improved properties such as charge rate. And then 90% of the lead that's produced in the US is currently used in automotive lead acid batteries for like conventional gas-powered vehicles. So as we start going from those gas-powered vehicles to electric vehicles, we're going to need to do something with all that extra lead. And so what if we could take that lead and use it in lithium-ion batteries instead? We're still using it in batteries, but it's a different chemistry in this case. So how does lead perform when you actually use it? So I made 4 different types of lead, all of the chalcogenide family. And chalcogenides are basically the group of the periodic table starting with oxygen and going through sulfur, selenium, tellurium. And so I've shown some cycles from that data there on the left, where you have the cycle index where each cycle is 1 charge and 1 discharge, and then the capacity that you got for that cycle. And so I show it here for 100 cycles. So these colored bars are different properties of the materials, and basically as you go up or down the group from oxide to telluride, the properties they trend good or bad. So for instance, as you go down the periodic table, oxygen is the lightest material, and you want light materials for your battery, so that's green. As you go down, you get heavier and heavier, so that becomes red as you get to the worst side of the property. So if you look at the capacity from this plot, you can see that you start out with lead oxide here at the top with the highest capacity. And that's because to calculate capacity, you divide by the weight of the material, so they're kind of inversely proportional. And as you go down, you see it follows the trend of the periodic table, where the highest capacity is lead oxide, and then it's the worst with lead telluride. In terms of stability, that trend reverses. So the lead oxide has a really rapid decline in stability here in the beginning, and you can see it starts to flatten out as you go down the group in the periodic table, and then lead telluride itself is pretty stable over the 100 cycles that I tested. I don't show the data here, but in terms of charge rate, it follows the same trend where lead oxide can barely be charged at even a slow rate, and the lead telluride can actually be charged pretty quickly without losing much of its performance. I was able to get a battery to charge in about 30 minutes without losing much of its capacity at all. But of course in engineering there's always trade-offs, and so of course the one that performs really well, the lead telluride, is going to be the most expensive. And that has to do with the abundance of the chalcogenide itself. So oxygen is relatively cheap, it's abundant, it's everywhere. Tellurium is pretty rare. And so here's how I could potentially hype this material if I wanted to. If you took a 2100 milliamp hour Samsung Galaxy S3 battery and you made it with this lead telluride material I talked about, you could charge your battery in only 30 minutes. It would only weigh about 3 dimes more, and it would only cost about $1 extra. Sounds pretty great. Why aren't we using this material? In reality, I only tested it for about 100 cycles. That's due to the limitations of being a grad student. I don't want to be here forever, so I have to kind of cut it off at some point. But really, you need to go about 1,000 cycles without losing more than 20% of your capacity in order for it to be something that you could use in industry. And then the cost, as I mentioned, so tellurium is about as rare as platinum. And so when I did these cost calculations, the dollar cost came from the prices of tellurium today. But if you started using a lot of tellurium to make these batteries, you would end up driving the cost up, and so it would eventually get a lot more expensive. So now we're going to look at lithium. That's the second material I'm studying. And so that one actually could have some practical benefits in the future because it's got the really high capacity and also the really low potential, giving it potentially the largest energy density. So just some motivation for why studying lithium. That article I mentioned before called it the Holy Grail, that part isn't hype. You could actually improve the capacity by about a factor of 10 over graphite. It's got the lowest potential, as I said, which would give you the highest energy density. It's the lightest of the elements that's used for energy storage, and so it would give you the lightest batteries. And it's the highest capacity of the known anode chemistries. And so this material really actually is pretty fantastic if we can get it to work. People have been trying for about 40 years and had no success. So as an engineer, safety is always the first concern we have, so I'm going to talk briefly about that. I like to always bring that up and keep it at the forefront of everyone's mind. So lithium reacts with air and water. That can create hydrogen flames. The electrolytes we use have salts that can hydrolyze to hydrofluoric acid, which is pretty dangerous. And then the solvents in the electrolyte themselves are flammable and toxic. So what we do is we work with all these materials in an argon-filled glove box, which is pictured behind me there. And so this argon-filled glove box has no air or water in it, and that serves two purposes. It keeps the lithium safe from the air and water, and it keeps me safe from the lithium. So let's say we wanted to take our graphite anode and replace it with lithium metal. As we move the lithium over from the cathode to the anode, we would expect that lithium would have a nice, solid, smooth, flat plating going on. But in reality, it's not flat or smooth. We get these sort of long dendritic growths, and if one of these lithium growths touches the other side, you get a short circuit. Electrons pass rapidly between the two sides and heats up, and that can cause a fire within your battery. And so I've got some pictures of actual dendrites down here, and they can come in all sorts of different shapes and sizes depending on how you charge your battery, what your electrolytes are. They can be kind of, it's a ball of yarn type shape down here. They can have really sharp needle-like shapes, or even this kind of fractal lightning shape over here. So this is what it looks like with a regular system if you cycle and you have dendrites present. If you think this looks pretty messy and unstable, it's because it is. So if we zoom in here, you can see that it's not a very flat potential like we would want, and there's all these sort of large spikes which are indicative of these dendrites growing and like little micro shorts basically happening. So what my research involved was finding an additive to add it to the electrolyte to improve the performance. And so a typical lithium-ion battery electrolyte will have about a concentration of 1 molar of a lithium salt. I added in this additive that was about 100 times less, 100 times less the amount of that salt. And you can see the results are pretty astounding. If we look at the zoomed in portion here, you can see that it's nice and flat. There's no voltage spikes during the entire 18-day test period. It's nice, flat, smooth. This is about as close to ideal as we can get with this system. So how does this additive work? In a typical system, your lithium ion will have about 4 solvent molecules kind of attached to it. And when you bring 2 of those to the surface of the lithium, they're going to react and form this red material called lithium ethylene dicarbonate. So I have it colored in red because red is bad. And so this material is porous, and that's why I'm showing these holes here. It's also insulating. So the lithium will only be able to deposit on the surface through those holes. And what ends up happening when you do that is you get these dendrites growing. And so that's what causes the dendrites. So once we add this additive, the additive ion only has 1 solvent molecule that attaches to it. And so that reacts in a different sort of chemistry to form this green material on the surface. So green is colored because it's good. And so the green material is a thin layer, and it doesn't have that porosity, it doesn't have the holes. And so when lithium wants to grow on it, it grows in a nice, smooth, even way. And we get the ideal system that we need for lithium to work as a metal. And so I wanted to look and confirm that these 2 materials were actually being formed on the surface. And so to do that, we use a technique called X-ray photoelectron spectroscopy. So the two different materials show up as these sort of curves here, where again, red is bad and green is good. And so the top curve shows the system without the additive. And you can see there's a lot of the red material and not so much of the green material. But once we add the additive in, with the second curve down here, the two curves flip and there's a lot more of the green material. So this just confirms that we formed that beneficial green material on the surface. So how would I hype this material? I would say something to the effect of the 40-year-old dendrite problem is solved, the holy grail is here. We can improve the capacity of our batteries by about 10, a factor of 10 by adding just a small amount of the salty electrolyte. The electrolyte typically costs about $500 per liter, and this would only increase that cost by about 50 cents per liter, which is about 0.1%. In reality, you need to test these for a lot longer than 18 days. So 18 days is a pretty long period by the literature standards, but it has to go a lot longer than that to actually be usable in an actual battery. We tested it at higher charge rates, and it didn't work. It still worked pretty well, but not quite as well. And so we would need to iron out some of those problems. And then even if we got it working perfectly, there's no manufacturing in place yet to use these lithium metal anodes. We couldn't just add this to the system overnight and suddenly be using these in our batteries. Manufacturing needs to be put in place to use lithium metal anodes because the lithium metal itself is so reactive. You would have to come up with a new manufacturing method to deal with that. So I think I've shown here a little bit about how easy it is as a scientist to kind of overhype your results. So you can be excited about your results. Like my lithium results I'm pretty excited about. I think they're pretty good. But be careful not to mislead people by leaving out selective information. So read news articles with a healthy dose of skepticism. So a lot of news articles aren't really out there to tell you the whole truth. They're there to make money. They want you to click on their headline so that they get ad revenue. So be careful when you're reading those headlines. Journal articles are a lot less likely to be full of this hype, but sometimes it's still there. Something I've seen a lot recently is authors will put a table with their results compared to a lot of the results of similar materials as a way to show that they are doing better than other people. And so it's kind of like a hidden sort of hype, but it's still there. If something seems too good to be true, it probably is. We've been seeing these headlines for batteries for a long time now, and none of them have come to fruition yet. And this doesn't just apply to the battery field. These are some other headlines I found just today talking about other sorts of things. So graphene is like marketed as this wonder material that's going to solve all of our technological woes, and apparently Glasgow University's found a cheap way to produce it, but I'll believe it when I see it. The creator of 5 Hour Energy wants to power the world's home with bikes. Apparently a Toronto firm thinks they can store energy with underwater balloons. These are very attention-grabbing headlines, but they probably won't ever materialize into anything. So it's always good to be skeptical. So with that, I'd like to acknowledge my advisors, Dr. Buddy Mullins and Adam Heller, the entire Mullins group, and then my undergraduate research assistant, Cody Pham. He helped me do a lot of these experiments. And then for funding, the Department of Defense, the Welch Foundation, and the IGRIT program. With that, I'll take any questions.
Hi, thank you for your talk. In terms of disposing these batteries, like there's always the talk about lithium-ion being, like not that great, and after, especially with electric vehicles, after 5 to 8 years, you need to dispose these batteries. Like, how do you see that being helpful with your research, or are you even focusing on different materials that would help that issue? Obviously, you only talked about the additives, but do you have any?
So in terms of lead, I think 97% of all lead is currently recycled. And so if you were to use that in things like electric vehicle batteries or grid storage, they're big enough that there are recycling programs in place already. So I think recycling in general is kind of a problem with smaller batteries, like in your cell phone. Like people don't want to recycle their batteries, they'll just toss them in the trash. I think with car batteries and bigger scale batteries, it won't be as much of a problem. It's kind of like when you go get your lead acid battery replaced in your car now. They take it from you and recycle it and give you a new one. I think something similar would happen with electric vehicles because you can't take a big electric vehicle battery and toss it in a dumpster. You're going to have someone else dispose of that for you. So I think once we get to these larger scales, recycling won't be as much of an issue.
Hey, Sean, great presentation. I like your slides. Question on the charge cycling degradation. So is that impurities and things that build up at the anode or cathode, some of those spikes that you're talking about, or just curious why some batteries, like you mentioned lead acid batteries for cars, it seems like a car battery lasts about maybe 3 years or so, and then you got to toss it out and get another one. My guess is it's based upon the charge cycling, 1,000 or 10,000 cycles, is it? Is there a way to improve that? I know one of your slides showed as you cycle up to 100 degradation for some of them, like I think it was the oxide one, but then like selenium or selenium had longer longevity at least. Any thoughts on that?
So it definitely depends on the material. There's all sorts of different degradation mechanisms. So with the lead, for instance, as you insert lithium into lead, it expands by about 400%. And just the constant expansion and contraction of those materials is very stressful and causes the particles to break apart. And so it degrades that way. The lithium itself has another degradation mechanism where, so when I showed that layer being formed in the lithium metal, that was during the first cycle. Every time lithium is taken away or added, more of that electrolyte reduction occurs. And so you basically get this layer of gunk that builds up on the surface. And that kind of kills everything over time. And there's different ways of dealing with each one of those. So the additive that I showed seems to help with that. But more long-term tests would be needed to see if it lasts over time.
I have a question. So what are the other researchers doing in this area, especially the idea of the additives? Are there any other additives that are being explored? And second part of that is, let's say you run this for more cycles. The second portion of your presentation sounded much more optimistic about the idea of adding the additives, and it's just a question of testing it for longer. Mm-hmm. So at that point, how do you expect it to get picked up? Let's say you run it for 1,000 cycles and say, or 100 days, and it does well. Like, what's the future steps? What's the next steps?
Okay. So other people have been working on lithium, like I said, for about 40 years, and there's been all sorts of approaches taken. So the electrolyte I use is a carbonate mixture. Other people have used ionic liquids and seen that dendrites were kind of suppressed. But again, ionic liquids are going to be very expensive. There's been all sorts of things. That Holy Grail paper that I cited, they put a sort of plastic protective layer to prevent those dendrites from growing. But again, that's going to be very expensive to install on an industrial level. And so there's been lots of work. In terms of if this were to kind of be successful in the longer term, what I think people usually do at a university is they would file for a patent, and then potentially a company would come and request that they work with you on that patent to pick up that material. So for instance, another guy in my group developed this germanium material, and so he filed for a patent, and then researchers at Argonne National Lab paid him to ship him some of that material, and they're studying it, and it could potentially be used in industry later. But it's a very long process. That's why I'm saying don't believe the hype. If they say it's going to come out in a year, it can take 5 to 10 years. Even if the material works now, it can take 5 to 10 years for that material to really make it to industry.
Thanks.
Hi, thanks so much. So I am not exactly an expert on battery tech, but I was kind of curious about a couple of things. Mm-hmm. So I read somewhere that one of the main things that a lot of researchers were focusing on was kind of like a spinel structure to like store the lithium. Mm-hmm. And I was kind of curious about the comparison between the two models, where you have like this one that kind of stacks up and grows, as compared to like a spinel structure which like stores the lithium inside some overarching lattice.
Yeah, so that's on the cathode side, and so the layered structure that I showed you basically have 2D diffusion. You can diffuse in either X and Y between those planes. Spinel is going to be, I think, I'm not quite positive on this, but I think it's basically more of a tunnel system. So you have a sort of 1D diffusion through those tunnels, and it's stored that way. But again, it's going to be, that plot I showed, it's going to be towards the left in terms of the capacity. It's going to be pretty low capacity just because you have to have so many of these other elements just to store like one lithium.
Okay. Yeah. Can I ask another question? A different question that I had was sort of related to past like issues with batteries, especially especially like electric vehicle technology. One of the biggest issues I remember was like voltage fade, where after each successive charging, the voltage dropped rapidly, and that's not an issue in this model.
So the way we charge it, we apply a constant current and kind of watch what happens to the voltage. So back on the lithium slide, it's kind of hard to tell, but there is like a slight, if you look here and compare it to here, there's a slight drop. But lithium metal itself has, by definition, a potential of 0 volts versus lithium. And so you won't really see the potential fade there. I think that's usually more of a problem on the cathode side, where as you start to degrade these materials, they kind of fall apart and your voltage drops a little bit.
Okay, thank you.
All right. Well, thanks a lot, Sean.
So how many, there is one more session of this one next week, right? It's done, this is the last one. Oh.